This on my phone. Anybody know? Utima? Yeah, maximize bonding, minimize repulsions. That's one. But anyway, they both come from valence bond theory and molecular orbital theory. Both come from QM. Do you know what QM stands for? Quantum mechanics. So they're both from quantum mechanics. They're just, I call it quantum mechanics light and quantum mechanics full. But anyway, we want to understand the bonding. Well, we don't really have to understand the quantum mechanics. We just look for simple physical things like precipitates. We memorize the solubility rules, that type of stuff. Gas former, stronger acid, weaker acid. So we're looking for reactions between ions. However, there are some molecular compounds that participate in metathesis reactions. The molecular compounds that participate are ammonia and ammonia-like compounds. Ammonia-like compounds are called the amines. Amines are organics that behave like ammonia. And how does ammonia behave? Well, ammonia is a weak base, sorry. Ammonia is a weak base. What do weak bases do in water? They partially dissociate or partially hydrolyze. They partially hydrolyze water. Hydrolyze means they break apart water. So ammonia and water, what do ammonia and water form? Ammonium ions and hydroxide ions. So that's hydrolysis. Well, if I have amines are ammonia-like compounds. So one amine might be this. Do you know what CH3 group is called in organic chemistry? Methyl. And so this is called methylamine. Now, how does methylamine differ from ammonia? Well, how it differs is rather than having a hydrogen, we have a CH3. And so rather than having a hydrogen, we have a carbon bonded to it. How does having a carbon bonded to a nitrogen change its electronic environment? Do you guys remember electrostatic potential maps and that kind of stuff? Well, this is what we're after. Well, it doesn't change it that much because hydrogen has electronegativity of 2.1, carbon has electronegativity of 2.5. And so replacing a hydrogen with a carbon doesn't really change things much. And so what this means is that methylamine will behave just like ammonia. Methylamine will hydrolyze water to form the methylammonium ion and hydroxide. And so we form little bits of ion. These little bits of ions react in metathesis reactions. And so this is how molecular compounds can participate in metathesis reactions. Well, there are other things we think about when we're looking at this. You know, in terms of structure, I see that something like this, it's just like ammonia, except now we have a CH3 here. And so what we're going to do is we're going to do more structural analysis of this. In terms of structural analysis, I see these two nitrogens are quite comparable. In ammonia and methylamine. These two nitrogens are quite comparable because, you know, the electronegativity difference is comparable, and therefore the electron density on nitrogen is comparable, and so therefore they should behave similarly. And so we look at those types of things, and we'll look at those in more detail when we get to acid-base reactions, but right now, let's take a look at the oxidation states. When I look at the oxidation states here, what's the oxidation states in ammonia? And so what goes first, nitrogen or hydrogen? Nitrogen at +1, that means, hydrogen at +1 followed by nitrogen at -3. And so this is nitrogen in the -3 oxidation states. Oxidation states I put in parentheses. This is +1, +1, +1. How about methylamine? What are the oxidation states here? Now, There are two ways that we do oxidation states in Chem 1A. You can do it based on the formula. If we do it based on the formula, we might have something like this. Have you seen Fe3O4 before? You've probably seen Fe3O4 in your homework in Chem 1A. This is very unusual compound because the oxidation state on oxygen is what? -2 gives a -8. That means the oxidation state on iron is +8/3. We need a +8 on 3. In other words, we have 4 oxygens, each at -2. And we have 3 oxygens. I'm tired. 3 irons. And so the net negative charge is -8. The net positive charge has got to be +8. +8 divided by 3 gives us 8/3 on each. Does that sound like a normal oxidation state? No. And so what's going on here is this. When we do oxidation states based on a formula like this, we get the average oxidation state. This is the average, +8/3. But I don't want the average. What I want is, I want to know what are the oxidation states on each. And so to get 3 irons adding up to +8, I just take 2 + 3 irons and 1 + 2 iron. And so this is a mixed cation. So, and this is called magnetite. It's a mineral. It's very familiar with geologists. The magnetite. This will average out to +8/3. Well, the same thing here. When we do oxidation states, what we typically want to do is we want to look at it atom by atom. To look at it atom by atom, I'm going to show you a different way of doing oxidation states. When we assign oxidation states, we make an assumption. Oxidation state is defined as the charge on an atom, assuming that the bonding is 100% ionic. If we assume the bonding is 100% ionic, then an 100% ionic bond, winner takes all. The winner is the more electronegative atom. And so the way we count electrons is this. Hydrogen versus carbon, who's more electronegative? Carbon takes all the electrons from hydrogen. Carbon versus nitrogen, who's more electronegative? Nitrogen takes those. So carbon ends up with this many electrons. And so looking at the oxidation state on carbon, well, it ends up with 2, 4, 6 electrons. Normally has 4, so it has 2 extra electrons. 2 extra electrons is going to give it 2 extra negative charges, which means its oxidation state is -2. And so the oxidation state of this carbon is -2. The hydrogens are +1 because they end up with nothing. What's the oxidation state on this nitrogen? Well, nitrogen versus hydrogen, nitrogen's going to win. And so it ends up with 2, 4, 6, 8. Nitrogen normally has 5, so it has 3 extra electrons. It's -3. And so this is +1. And this is +1. And so we see that both of these are kind of similar in the respect that nitrogen has a lot of negative. In Chem 1A, I would call this compound electron-rich. I call it electron-rich. Electron-rich compounds are flammable. And so something like methylamine, I'd watch out because this can combust. Ammonia can combust. It should be flammable. Versus this. Is this an amine? NF3. Is this an amine? Yeah, it looks like it. If I take this and react it with water, it looks like I'm going to form kind of ammonium analog and hydroxide, right? But when I see this, I say, no, this is definitely not an amine. This is totally different than this. In what way? Yeah, when I look at this, fluorine versus nitrogen, who wins? Fluorine gets 1 extra. Fluorine. So each fluorine is -1. That means nitrogen is, well, nitrogen ends up with 2 electrons. It's supposed to have 5, so it ends up 3 electrons short, or plus 3. Do you think a nitrogen with a plus 3 oxidation state is going to behave the same as a nitrogen with a minus? No, totally different. This is not a base at all. And it's going to behave, so this is not an amine. And so amines are going to have certain common features. Not an amine. There are different ways we can analyze these things, but let's see. So ammonia and amines can also participate in metathesis reactions because they're going to form some hydroxide. The hydroxide likes to form precipitates with certain metal ions. There are a lot of insoluble hydroxides. There are lots of different precipitates, so let's take a look at some of the precipitates. And so when we're looking at what's going to precipitate, we need to have the solubility rules memorized. I'm just curious, how many of you didn't have to memorize the solubility rules in Chem 1A? Everybody memorized them? Okay, that's good. I like the solubility rules in the lab manual. I think they're a little easier to memorize and it doesn't make that big of a difference versus the textbook. And so the solubility rules in the lab manual go like this. Rule 1, group 1 and ammonium compounds are all soluble. Okay, these are rules. What's the difference between a rule and a law? Well, a law would be much more absolute than a rule. A rule has too many exceptions. You know, law would have much fewer. But here, there are some exceptions. You know, sodium ions, you can precipitate those with the uranol and acetate ions. And so there are some precipitates, but those are rare. And so what we can say is group 1 and ammonium compounds are all soluble except for some rare exceptions, which we're not even going to worry about. Rule 2, do you remember it? Nitrates, acetates, and chlorates are all soluble. Rule 3, chlorides, bromides, iodides are all soluble except silver, lead, mercury. Rule 3, sulfates are all soluble. Silver, lead, mercury, calcium, strontium, barium, etc. And so the easiest thing to do is just go back through those and write them over and over until you got them memorized. All right, that's for precipitate. For stronger acid to weaker acid, typically most people memorize the 7 common strong acids here. You know, all other acids are weak. But there are exceptions. You know, there are acids that are stronger than the strong acids here called superacids. We aren't going to worry about those too much, but you should know these. And for the other acids, we just rank them. You know, there's a leveling effect for strong acids, so I don't really care about the order here because of the leveling effect. But the weak acids, we just look up on the table. Some of them we could figure out, like water. Water is very weak. So, you know, acetic acid versus water, acetic acid would be stronger. What a lot of people don't memorize are the strong bases. What are the strong bases you have memorized? A lot of people will say, oh, sodium hydroxide, potassium hydroxide. But that's too limited. You know, the strong bases are the soluble hydroxides. But there are stronger bases than hydroxide that you do have to know. What are the stronger bases than hydroxide? Sulfide, amide, oxide, hydride, methide. These are all more powerful than hydroxide. These are the strong bases. Like the leveling effect for strong acids, there's a leveling effect for strong bases. Now, the leveling effect, let me talk a little bit more about the leveling effect. The leveling effect says this. The strongest acid that can exist in water is hydronium. Any acid stronger than hydronium is unstable in water and will react immediately. So this is why we say HCl. HCl is a strong electrolyte because HCl immediately is going to dissociate or hydrolyze with water. HCl itself doesn't exist. You aren't going to find HCl molecules in water. Or you might, but that's a rare coincidence, and it should rapidly break apart or reform. And so the HCl is unstable because the HCl is going to ionize or hydrolyze 100% to H plus in chloride or hydronium in chloride. Does that make sense? And so all these do the same thing. So all these, if you have HI versus HCl, well, HI is stronger, but both of them are going to yield the same thing in water. The same amount of hydronium for a given concentration. The leveling effect for strong bases goes like this. All these bases are way too strong to exist in water. Now what bases do is they don't ionize, bases hydrolyze. That is, they attack water. And so for example, sulfide will immediately attack water to form hydroxide. Hydroxide's stable, it can exist in water, just like hydronium is stable. But sulfide itself is unstable. Amide, same thing. Amide will attack water, form hydroxide. All these will form hydroxide. This is the most stable base. And so there's a leveling effect for strong bases. The leveling effect is a bit more complicated, as we'll see in our calculations later on. Okay, the gas formers you just memorized. You know, carbonic acid decomposes in water and CO2. Sulfurous acid decomposes in water and SO2. Ammonium hydroxide is unstable. That decomposes in ammonia and water. Some metathesis products form outright. So if you add acid to sulfide, you're going to get hydrogen sulfide. If you add acid to a cyanide mineral, you'll get hydrogen cyanide. Both of these are quite toxic. So you want to avoid contact between acids and sulfides and acids and cyanide, etc. There are other gases that could potentially form. But these are some common ones. You have these slides. And so we did this example already, calcium carbonate and sulfuric acid. We look at the next one. In the next reaction we're going to look at is potassium sulfide and acetic acid, but we'll do that after our break. So let's take a 10-minute break, and we'll complete some examples, metathesis reactions.